All right, let's get going. I was imagining we'd talk more about partial derivatives and maybe some tangent plane linearization kind of stuff. And then if we have time, we will move towards the chain rule. So I know last week we briefly touched on one example of partial derivatives. Let's do a few more. Let's say we have this kind of function. Let's actually write partial derivatives. So let's say we have a function of x comma y, and it's equal to x to the 6th plus y to the 3rd plus x to the 4th times y to the 5th. And we want to find lots of things. So we're going to find the first partials and the second. So let's talk about finding the first partials. And again, there's a couple ways of writing this. You can either write the first partial with respect to x as del f del x, but people get tired of writing so much. So instead we often write this as fx. And I should just mention fx is the kind of right way to say it. You shouldn't say f of x. You could say f sub x if you really wanted to, but really the way people are going to say that is fx. Like that's the way I'm going to say it, because that's what I was taught, right? Or you can say del f del x. And then the whole idea is just that we are treating x like a variable and everything else like a constant. So y is a constant, any other variables are constants, regular constants are constants. So here the derivative of x to the 6th is going to be 6x to the 5th. The derivative of y cubed is going to be 0. And the derivative of x to the 4th times a constant is going to be 4x cubed times that same constant. Now, I know that since I'm going to eventually take another derivative of this, I want to simplify this just to make it look a little nicer. There's not a lot of simplifying to do here. Really, it's just not writing the 0. Everything else is kind of simplified as much as possible. So we could write this as fx is 6x to the 5th plus 4x cubed y to the 5th. So in the same sort of way, why don't you all find del f del y or fy? Go ahead. You all on Zoom too. You can even type it in the chat if you want to type the answer in the chat. You don't have to, but you could. So let's see. So for fy, the derivative of x to the 6th is 0. So I'm not even going to write it down. The derivative of y cubed is 3y squared. And the derivative of x to the 4th times y to the 5th is x to the 4th times 5y to the 4th. And I would probably write that as fy equal to 3y squared plus 5x to the 4th y to the 4th. Okay, first partials, not too big a deal. Second partials, we need to be a little bit more, no, second partials are also not too bad. So how many second partials are there? Well, there's 4. I mean, really, there's only 3, but there's really 4. So there's this one. There's del squared f del x squared, bless you, or written as fxx. It's the partial with respect to x twice. So what we're going to do to find the second partial with respect to x is we're going to take the first derivative with respect to x, or the first partial derivative with respect to x, and just take the derivative of that with respect to x again. So if you really wanted to be notationally correct about it, you could say it's going to be the partial derivative with respect to x of the partial derivative with respect to x. I don't think you need to write all this out, right? If I was doing this, I would just, here's what I would actually, so let me finish this and I'll write what I would actually write. So I'm going to find, I mean, this is 5 times down, you get 30x to the 4th, and then the derivative of 4x cubed is 12x squared. The y to the 5th constant just sticks around. So I get 30x to the 4th plus 12x squared y to the 5th. But I will tell you, if I was actually like a student doing this as my homework assignment, I would just write, okay, there's my fx, and maybe even over here, I'd say, okay, now I'm going to see that fxx is just 30x to the fourth plus 12x squared. You don't need to write that. You can, and some people might. All right, there's a couple more. There's actually 3 more. The ones we typically think of first are the second partials with respect to x and the second partials with respect to y. So del squared f del y squared, or fyy, is going to be the partial derivative with respect to y of the partial derivative with respect to y. I'm taking the derivative with respect to y of 3y squared plus 5x to the fourth y to the fourth. And when you get 6y plus, let's see, the derivative of 5x to the fourth times y to the fourth is going to be 5x to the fourth times 4y cubed, which is going to give me 6y plus 20x to the fourth y cubed. But there are 2 other partials we can find. And this is where notation gets a little funky. I think I need more paper here. So I want to find del squared f del x del y, the mixed partial derivative. And this says that we do y first, or I should say we differentiate with respect to y first, and then x second. So if you want to write this as 2 derivatives, it's the partial with respect to x of the partial with respect to y. And now here's the bummer. At least I think it's a bummer. If you're using the other notation, the subscript notation, we write this as fyx. So I just want to be super duper clear. This says we do y first, x second. This says the same thing. This says we do y first, x second. That's just the way it is. Kind of annoying, but that's the way the notation has been decided upon by someone who isn't me. Okay, so it's still not a big deal though. So if I'm doing y first, I'm just going to look for the partial with respect to y, which is right there, 3y squared plus 5x to the fourth y to the fourth, and I'm going to differentiate that with respect to x. So the derivative of 3y squared, in fact, let me write it down. I'm going to do del x of 3y squared plus 5x to the fourth y to the fourth. So now I'm treating y like a constant, and I'm getting the derivative of that is 0, and the derivative of 5x to the fourth is 20x cubed multiplied by the constant y to the fourth. And we can go the other way. We can also find the other mixed partial. Del squared f del x del y, which means, oh, I didn't write the other one. I wrote the same one. Sorry about that. Not what I meant to do. I meant to write del squared f del y del x, meaning we're going to differentiate with respect to x first, and then with respect to y second. So that's going to be the partial derivative with respect to y of the partial derivative with respect to x, or using the other notation, fxy, x first, y second. So here's your derivative with respect to x. I'm just going to write it, I'm going to copy it from up here. It's 6x to the fifth plus 4x cubed y to the fifth. That is our partial with respect to x. And then we're going to differentiate that with respect to y. The derivative of 6x to the fifth with respect to y is 0. And the derivative of 4x cubed times y to the fifth, 4x cubed is a constant, or x cubed. Terrible. And the derivative of y to the fifth is 5y to the fourth. And we simplify that, look what we get. We get 20x cubed y to the fourth. And what do we notice? So here's the thing that's mostly true. And you say mostly true. So it is true mostly that the second partial with respect to f, the mixed partials, I should say, are equal to each other. So this is true most of the time, which I know doesn't sound very reassuring. So here's the real truth. This is true for any function you're going to encounter in this class. For that to not be true, someone has to make up some really kind of bizarre function where it doesn't work. Like it has to be some weird piecewise thing. So if you see like a normal function where you just go like f of x, y equals x's and y's mixed together and you don't see a piecewise function, not going to be a problem. Just so you all can see real quick, I think I've got an example here. Not that you need to know this, but I want you to see it just so you know what something that didn't meet this would look like, so you're not too worried about it. Where are you? Sorry, 1 second. I have to find it. Oh, there we go. It's right there. It was right there. Brain, come on. Let me just. There we go. I see it now. So here is a function right there, f of xy equal to xy times x squared minus y squared over x squared plus y squared when xy isn't 0, 0, and equal to 0 when xy is 0, 0. That kind of function. This is like the simplest example of a function where fxy doesn't equal fyx. So if you're seeing something at least this complicated, meaning it's got to be kind of a weird piecewise thing, it might be the case that they're not equal to each other. But I will tell you, we don't really see things like this in this class. So I wouldn't worry too much about it, or really at all. So most of the time, you are pretty safe just assuming that fxy and fyx are equal to each other. Which is nice. That means you can kind of check to see if you've done it right by doing it both ways. Okay. What else to say about this? Questions before we move on to some more examples. All right, let's see what we got here. Sure, let's do that. Well, let's say our function is, f of x comma y equal to x minus y over x plus 3y. We want to find some partial derivatives. So let's go ahead and find fx. It does get to be a very just kind of like routine calculation, right? You're not doing anything that special. You're just pretending like, in this case, y is a constant. I'm still going to use my normal derivative rules. I'm just thinking of one extra tiny little piece here. So in this case, I'm using the quotient rule. It's going to be the bottom times the derivative of the top. Okay, what's the derivative of the top? You can tell me on your fingers. Is the finger answer? What's the derivative of the top? It is just 1, right? Minus the top times the derivative of the bottom, which is also 1. Or I could say 1 plus 0 if you want to be more right. Thinking about what's happening there. Derivative of x is 1, derivative of 3y is 0. And then finally, divided by the denominator squared. And here's what I would say about these. If I was just finding the first partials, I would leave this alone. I wouldn't bother simplifying it. But since I know I'm going to ask to find the second partials, I'm going to go ahead and simplify it to make finding the second partial not as terrible. So simplifying this, I have x plus 3y minus x plus y over x plus 3y squared. And those x's cancel, and I end up with 4y over x plus 3y squared. Or maybe if I prefer later on when I take the derivative of that, I might prefer to write it as 4y times x plus 3y to the negative something. Maybe that's going to be an easier way to differentiate it for me. I don't know. All right, why don't you all find fy? I'll give you a minute and 20 seconds. All right. So same calculation, quotient rule again. It's the bottom times the derivative of the top, which is now -1, plus the top. Sorry, not plus, minus the top, excuse me. Minus the top times the derivative of the bottom, which is 3, all over the denominator squared once again. Simplifying this, let's see what we've got. We've got a -x minus 3y minus 3x plus 3y, all over x plus 3y squared. It looks like those 3y's cancel. So I have a -4x over x plus 3y squared. Or maybe a -4x times x plus 3y to the -2nd. All right. So it's not that these are particularly challenging, it's just a little tedious. Like finding the next derivatives is going to be worse because it's just. Let's go ahead and find them both. Yeah. Which way do I want to do this? Either way is kind of fine. Oh yeah, that's not so terrible actually. So let's go ahead and yeah, I think I'm going to write it this way because if I think about fx being this, fxx, if I'm differentiating this, if I'm differentiating this with respect to x, I don't really have to think about the 4y. If that 4y, as far as I'm concerned, is a constant. So for fxx, that 4y is going to hang out. And then we're going to have the derivative of some stuff to the -2nd power. And the derivative of that is going to be -2 times our stuff to the -3rd power times the derivative of the inside, which is just. Yeah, question. So I'm differentiating this. So when I have some stuff to a power, right, the power comes down and the new power is -1, and -2 minus 1 is -3. Again, just to kind of show you both ways, we could have also done it as a quotient rule. If I'd done it as a quotient rule, I would have gotten the bottom, x plus 3y squared, times the derivative of the top, which is 0, because it doesn't have any x's in it, minus the top, which is 4y, times the derivative of the bottom. The derivative of something squared is 2 times the something to the 1 less power times the derivative of the inside, but the derivative of x plus 3y is just 1 plus 0. All divided by the denominator squared. So x plus 3y squared is x plus 3y to the 4th. To me, that looks more complicated. But they're both the same, right? If I simplify either one of these, -3 times 4 is -8. I get -8 times y times x plus 3y to the -3rd. And here, this term totally goes away. That's just 0. And I have a -4 times 2. I have a -8y. And x plus 3y to the 1st divided by x plus 3y to the 4th is exactly x plus 3y to the -3rd. So either way you do it, you're going to get the same answer. It's going to look a little different along the way. Finding the second partial with respect to y is going to be a similar process. So if I look at my fy there, then fyy, well, again, I'm treating -4x like a constant. So -4x times the derivative of this is going to be -2 times my stuff to the -3rd power. But then what do I need to multiply by? Show me on your fingers. What do I need to multiply by? It only takes one hand. You don't need both. It's not that big a number. Okay, think about the chain rule. We're using the chain rule. What do I have to multiply by? Yeah, exactly. That, yes, exactly. Yes. This many. Right? Because I'm taking the derivative of the inside stuff, and the derivative of x is 0, and the derivative of 3y is 3. I should say I have to take the derivative with respect to y of the inside, and the derivative of x is 0, and the derivative is 3. And if we want to simplify this, 3 times -2 times -4 is going to give me a positive 24 times x plus 3y to the -3. And lastly, the mixed partials. So let's go ahead and find fxy. So for fxy, it is going to be a little bit more work, right? I actually am going to have to really use the chain rule, the quotient rule in earnest here, because both my numerator and my denominator have the variable I'm differentiating with respect to. Right? I'm taking the derivative of fx with respect to y. So here I'm going to get the bottom, x plus 3y quantity squared, times the derivative of the top, which is 4, minus the top, times the derivative of the bottom, which is 2 times x plus 3y to the first, times the derivative of the inside stuff, which again is 3, all divided by the denominator squared. So it's going to be x plus 3y squared squared. That looks kind of awful. There is one thing which, so if we're living in the world where we're simplifying these things, because sometimes you need to simplify them, especially like if you're this one less so, but so if you're trying to find critical points at some point, which you eventually will be asked to do, is to find critical points to these things. You're often setting these partials equal to 0. And so to simplify this, whenever you have a quotient like this and the power is higher than 1 to start off with, like if I'm differentiating something and the denominator is something squared, or something cubed, something to the 4th, that factor is always going to be able to be factored out to some level. So I see in the numerator here, I have an x plus 3y squared here, and I have an x plus 3y to the first here. And I can definitely factor out an x plus 3y to the first. I can also factor out what? It's an easy thing to see there. An easier thing to see. What number can I factor out from the top for sure? 4. There's a 4 there, there's a 4 there. If I pull out a 4, which makes sense because we started off with a 4 in the numerator at the very, like we could have just factored out that 4 from the very beginning. It might have been a better choice. But if we pull out a 4, we're left with and an x plus 3y. From this first piece, we're still left with n x plus 3y to the first. And from the second piece, we factored out a 4 and we factored out an x plus 3y. We're left with a 3 times 2 times y. All over x plus 3y to the 4. Simplifying just a tiny bit, we can cancel an x plus 3y here and an x plus 3y there. And we're left with 4 times inside here, x plus 3y minus 6y is x minus 3y. And the denominator is x plus 3y to the 3rd. And now what you all should do, not right now, but later, is later on, I encourage all of you to find the other mixed partial, fyx, meaning you'll take the derivative with respect to x of -4x over x plus 3y squared. I encourage you to do this, to do the simplifying, and eventually, if you do it all, you should get to the same place. 4 over x minus 3y over x plus 3y squared. Good practice. But I don't think we need to do that now because I think it's something more I think we'll do. Questions so far? Good so far? Questions from the Zoom people? By the way, for the Zoom folks, just in case I missed it, here's the attendance form one more time. Please do fill it out. The partial derivatives, not too terrible, right? It's just your usual derivative rules, and you are pretending like one or more of your variables are a constant. let's look at one more example where things get a little, just a little more challenging. Not a lot. You don't have to have a function of just two variables. You can have a function of 3, 4, any number of variables you want, really. So we could have something like f of x, y, z equal to, I don't know, x cubed times sine of 3y plus 4z squared, for example. And we can find all the partials. I do want to point out that when we're thinking of just f of x, y, if we're thinking like in a physical way, we're kind of thinking like z equals f of x, y, where z is like the height in your three-dimensional graph. That meaning is kind of gone away now. Right? We're no longer thinking about that because we've lost that. But if you are thinking just as a function of a, sorry, just thinking of a function of just x and y, there's often that three-dimensional graphical interpretation that you want to kind of be aware of in the back of your mind. It's going to come back up in a minute. So I want to find fx. I'm just going to pretend like y and z are constants. So as far as I'm concerned, all of that is a constant. So I have x cubed times a constant. And my derivative is 3x squared times the constant. Not too terrible. Fy same idea. Now we're treating x and z like constants. So what I see now for my function is a constant times sine of my variable plus a constant. That's what I'm looking at. And so if I'm going to take the derivative, this constant multiple just hangs out. And what's the derivative of sine? Right. Or I should really say the derivative of sine of some stuff is cosine of the stuff times the, right, exactly. That's like if I say stuff, the answer is derivative. Like I'm always looking, right? If I say stuff, it means we're using the chain rule. Right? If you've got something that's more complicated than just your variable, we know we're always going to have to, if we're differentiating, eventually multiply by its derivative. So the derivative of sine of some stuff is definitely cosine of that stuff. Come on in. And then we have to multiply by the derivative of that stuff. What's the derivative of 3y? What's the derivative of 4z squared? Oh, you're so close. If I was differentiating with respect to z, that would be totally correct. But since we're differentiating with respect to y, the derivative of 4z squared is right. Be careful there, right? It's just, we're still thinking about y being the variable and everything else being a constant. Okay. So I want you all to do the last one. Find fz, the partial with respect to z. Oh, I should look and see if that's a thing. Question.
So you said the derivative of the sine and stuff because they're y.
Right, because our variable was in the thing.
Versus the one, the first one.
Right. Right. So like, for example, and that's actually, you're asking a good question. Let me kind of address it real quick here. If I'm back in my one variable world for just a second, if my function is like x to the third times sine of 2, I don't know what sine of 2 is. but I know it's not a variable, right? It's something that's not, you can plug it into your calculator and get some dumb number, like that's less than 1. It'd probably be, I don't know, it's probably close to positive √3/2-ish. Not the point. The point is, as far as anyone cares, this is a constant. But what I'm really trying to point out here is that a function of a constant is still a constant. So sine of 2 is a constant. Sine of 3 is a constant. The square root of 9 is a constant. Natural log of 7 is a constant. If there isn't a variable in there, it's a constant. So in the same sort of way, sine of all of this, if we're thinking about x being the variable, sine of all of this is a constant. So when I differentiate this, right, f prime of x is still 3x squared times my constant. Versus if my function was, say, pi times sine of 3x plus 1, then the constant's over here. I mean, but there's still some constant stuff happening in there too, but there is a variable in there. So I have sine of my variable. When you differentiate that, well, the constant multiple hangs out, and the derivative of sine of some stuff is cosine of the stuff. Whoops, cosine of all the stuff, James, cosine of 3x plus 1 times the derivative of the inside stuff, which is just space. So hopefully that kind of makes things more clear. That's a good question. I like your question. So back to this last one, if we're doing the partial with respect to z, we're saying, oh, I have sine of my variable somewhere in there, even though there's some other stuff in there too. When I differentiate it, the constant multiple out front just sticks around. And the derivative of sine of some stuff is cosine of the stuff. Notice the stuff doesn't change, right? If you're doing the chain rule, the outside function we differentiate, the inside stuff we leave alone, and then afterwards we multiply by the derivative of the inside stuff. So we're going to multiply by, okay, I'm trying to check you guys again. What's the derivative of 3y? And what's the derivative of 4z squared? And then you could simplify this, but I think it's just fine as it is. There's something there I wanted to say. Oh, I know what it was. So just to point out, if you really, really wanted to, I don't recommend it. You could use the product rule here instead, but it's not really great because essentially you have a constant in front. So I just want to point out that if we find fz, for example, using the product rule, and I just want to point out what's happening here. So here's our function, f of x comma y comma z equals x cubed times sine of 3y plus 4z squared. And I'm thinking of like, this is my first piece, this is my second piece. And when we do the product rule, we get the derivative of the first piece. Okay, what's the derivative of x cubed? Oh, sorry, I got a little ahead of myself here. I shouldn't say that. I shouldn't say this is equal to its own derivative. That's terrible. Let's do this down here. Okay. So now, if I'm finding the partial with respect to z, what's the derivative of x cubed? It's kind of a trick question, I guess, but not really. Is x our variable? No. So what's the derivative of just x cubed all by itself? It's 0. Now I know it's going to hang out, but hold on. So you're going to get 0, right? That's my u prime. U prime. Who picked u and v? Why did they pick letters that were so close to each other? I don't know, but that's just what they did. Times the other stuff, sine of 3y plus 4z squared. That's my v. And then we add and we differentiate the other way, meaning we differentiate the second thing, we leave alone the first thing. So I'm going to get x cubed left alone, that's my u, times v prime. And the derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. So it still works out the same because you get all this just goes away. It's 0 times whatever is 0. And here you're left with, oh yeah, your x cubed, your constant just hanging out times the derivative of the rest of it. So usually we don't do it this way, but some people think of this as a product rule and certainly can do it that way. It's totally fine. It's just, to me, it feels like more work than you really need to do. Okay. So what time we got? Got lots of time. Cool. Let's go ahead and talk about some linearizations and tangent planes. All right. So let's go back to 17A for a minute. So recall, meaning I'm going to remind you from your 17A class. So from 17A, at one point we learned that the equation of a tangent line, I'm going to emphasize the line part there, to your function y equals f of x at the point x naught comma y naught. Well, first of all, looks like this. I don't actually want to draw it yet. Is the following. It's y minus y naught equals your slope times x minus x naught. I'm just using the point slope form. So I do want to draw a picture though, because I like that picture. So if our function looked, I don't know, something like that. And we wanted to say find the equation of the tangent line at the point x naught comma y naught. Well, the slope of that line is just the derivative at that point, f prime of x naught. So hopefully that helps you maybe see it a little bit better. Oh yeah, I really am just using the point slope form. Y minus the y coordinate is equal to the slope times x minus the x coordinate. For some reason, somebody decided we should use different letters at some point to do this a slightly different way. So people like to write this as, well, I'm just going to do it the nicer way because this is what we're eventually getting at. I want to solve for y. So y equals y naught plus f prime of x naught times x minus x naught. You might have seen someone write it in the following way. Just to be super clear, you can totally write it this way. You might have seen someone say, though, instead of calling this point x naught comma y naught, I want to be difficult and call this point a comma f of a. And so instead of using x naught y naught, I'm just going to use a and f of a instead of x naught and y naught. And so I could write y equals, instead of y naught, I'm going to use f of a. Instead of f prime of x naught, I'm going to use f prime of a. Instead of x naught, I'm going to use a. Literally the same formula. Just like use different letters for it for some reason I can't fathom, to be perfectly honest. Feels like we're making it more difficult on purpose. So you might have you might not remember this very well. It's not like the most important thing in 17A for a stretcher, but the thing we often use this for is for approximating things. For example, we're going to do two things. We're first going to find the linearization. Okay, linearization, fancy word for the tangent line. You're just saying this function, I want to approximate it with a line near that point. So if you like zoomed way into this and got super, super close to that point right there, the graph kind of looks like a line. Like if you get really close enough to any graph, like and zoom into some super small section of it, unless it's a very wild looking graph, any graph close enough in is a line, right? Or at least the small section of it is relatively linear. That's what we're saying. Saying, oh, this point here, or right, like from maybe like from there to there, the graph is pretty linear. So that's what we're going to do with this. We're going to say, we're going to find the linearization, meaning the straight line approximation of something that's not a straight line. And I have decided on f of x equal to the square root of x at, and now here's where it's important to pick something nice. You're almost always going to be linearizing a function at a place where it's easy to evaluate it. So I'm going to pick a nice square number because those are the kind of numbers that are easy to plug into a square root. So we're going to linearize this to x equal to 9. Sorry, a equal to 9. Or x not equal to 9, whatever your preference is. And then we're going to use it being the linearization, to approximate the square root of 10. Now you might ask, why would anyone do this when you have a calculator? And I would say, good question. I don't have a good answer for you. Other than once upon a time, people didn't just have calculators that could calculate these things. And this was a valid method of approximating something with relatively good accuracy without doing too much work. So let's do it. So first of all, let me draw a picture and draw a decent square root function. And let's pretend like 9 is right about here. Square root of 9 is 3. And so I'm trying to figure out what the equation of this line is. Now I want to point out, the closer you are to 9, the better this line is as an approximation of the function. But as you move further and further away from 9, like we move way out here, right? The function moves further and further and further away from the line. So the closer you are to 9, the better an approximation this gives, the further away from 9, or whatever the point of approximation is, the worse the approximation. Okay, so let's find the linearization, aka the equation. I'm just going to use the formula, which is that the linearization, which we often write as L of x, capital L for linearization, we're not very original over here, is going to be f of a being 9, plus f prime of a times x minus a. So all I really have to do is find f of 9 and f prime of 9. That's not too bad. My function is the square root of x. So f of 9 is just the square root of 9, which is 3. I do need to find the derivative. Okay, so my derivative here, if my function is x to the 1/2, my derivative is 1/2 times x to the negative 1/2. Or as I would probably prefer to write it, 1/2 times x to the positive 1/2, or really actually 1/2 times the square root of x. That's my preferred way of writing the derivative of the square root of x, but they're all equivalent to each other. So if I want to find f prime of 9, f prime of 9 is going to be 1/2 times the square root of 9, which is 1/2 times 3. So that's the slope of this line. This line has a slope of 1/6. We're not quite done with the first part. We still have to write the equation of the tangent line. So I'm just going to take this formula and plug in the numbers. So my tangent line is L of x, or f of x, but I'm going to write L of x. Especially because I've already used f of x. I've used a different letter like g of x, not f of x. Is going to be f of 9, so 3 plus 1/6 times x minus. Here's a thing worth noting. You could totally write this in mx plus b form, right? You can distribute the 1/6, get something, add 3 to it. You shouldn't. The point of writing it like this is it's going to make it easier to calculate the thing you're being asked to calculate. So if you're finding a linearization, whether it's a linearization of a function of one variable or very shortly 2 variables, you're going to see that leaving it like this is actually to your benefit. Because now what we're going to do is we're going to plug in 10. We're going to estimate the square root of 10. Well, I know that this is, and I should actually point out, right, this linearization is an approximation of the function, the square root of x. What we're really saying is the square root of x is equal to this, kind of. It's close to it. At least if we're close to 9, right? If you're way too far from 9, it's a problem. If you're close to 9, 10, look what happens. When I plug in 10, so I want to point out, you guys all watch this real closely here. The y coordinate there is the square root of 10. I don't know what that is. It's okay. I'll try again. It happened in my previous class too. It happens all the time. It happens. I like talk to my watch. It's like, oh, okay. But what we're actually going to do is we're just going to go up a little bit higher to the point on the line. Because that point there is really close to the other one, right? There's not a lot of difference there. That's our error. And this point here is 10 comma L of 10, whatever L of 10 ends up being. So here's what we're going to say. We're going to say that the square root of 10 is approximately L of 10. And you probably can't say that right. We're going to say that the square root of 10 is approximately L of 10. And then we're just going to plug in 10 to this function, to this line, and get 3 plus 1/6 times 10 minus 9, which is 3 plus 1/6, which if we want a decimal just to kind of compare it, is equal to 3.166666 forever and ever and ever. If you're curious, the square root of 10 on a calculator, the actual decimal approximation of it is, let's see here. I always hate when you do that. Let's see. Square root of 10, should know this by now, is, so actual square root of 10 from the calculator is approximately 3.1662277 and so on. So our approximation is good for the first 3 decimal places. That's pretty great without doing a whole lot of terrible calculations. So that's kind of the idea behind these linearizations, is that you can use them to approximate a function that is otherwise hard to calculate. Like, I don't know what, I mean, there's other ways of approximating the square root of 10, but this is one that is fairly easy to do, doesn't require too much time or effort. Okay, so we're going to extend this idea to functions of 2 variables. And what I really want to say is that for a function of 1 variable, you're finding the tangent line to a point. For a function of 2 variables, what we're doing with our approximation is we're finding the tangent plane to a surface. So it's always harder in 3 dimensions, but if you imagine, I'll draw something that's kind of nice. So just for example, my favorite function, 2 variables, f of x y equal to 9 minus x squared minus y squared. We can find, I'm just going to draw it first. So here's my thing. And specifically, I'm going to look, just to make it easy to kind of see and draw, I want to find the equation of the tangent plane at the point 0, 0, 9, meaning at the top. This one's going to be extra easy by design. Okay, so let me ask you all. It's the very top of the mountain. And I want to draw a plane that just touches that, or I want to have a plane that kind of sits just at that point and doesn't touch any of the rest of the graph. So should the plane tilt left, or tilt right, or tilt back, or tilt forward, or not tilt at all? It's then a not tilt at all. And here's the thing: when you have essentially what's a maximum of a function on the surface or a minimum, the tangent plane is always a horizontal plane. Because if you had a plane that was tilted one way or the other, it would kind of cut through part of the surface. And tangent things should only touch one point, at least in their local kind of tangents. So I'm just going to tell you all right now, here's the tangent plane. And it cuts through it, there's that point there. So like, there's my tangent plane. Well, great. That's nice when it's easy, but how do we actually find the equation of the tangent plane? So here is the way to find the equation of the tangent plane in general. AKA the linearization of your function at a point. Well, it's literally the same equation. We're just adding an extra piece. So I'm just going to go back for a second. So the equation, whoops, for 2 pages, 1 second here. So I'm going to take my y minus y naught equal to f prime of x naught times x minus x naught. I'm going to add another piece on, meaning I don't have just the derivative in the x direction now. I also have a derivative in the y direction. So here's what we've got. I'm going to call this for a second z equal to 9 minus x squared minus y squared. And my tangent plane equation, check this out. Instead of y minus y naught equal to the derivative times x minus x naught, it's going to be z minus z naught equal to, well, I've got two derivatives. I've got the partial with respect to x and the partial with respect to y. So the partial with respect to x at x naught comma y naught times x minus x naught plus the partial with respect to y at x naught y naught times y minus y naught. It's literally the same idea, just extended by a dimension. Now, typically, we don't write it this way. We're going to isolate z and then replace it with L of xy. So we're going to say that the linearization here is L of xy, which is just taking the place of z. And it's equal to your z naught, but z naught is just what you get for z when you plug in x naught and y naught. So we're going to say that that's f of x naught comma y naught plus all this other stuff. The partial with respect to x times x minus x naught, and the partial with respect to y times y minus y naught. It's kind of a bit lengthy, but it's really not that different than the thing we did before. It really looks a lot like, where'd you go? Sorry. It really looks a lot. I didn't actually write down the linearization formula, I guess. Fine. Sorry. It looks a lot like this one here. Like y equal to y naught plus f prime of x naught times x minus x naught, just with an added kind of second piece here. For this particular function, it's going to be very kind of unexciting at this literal point. So let's see what we get. So for this function, if I'm plugging in 0 for x naught, 0 for y naught, and my z naught is 9, well, let's see. F of x naught, y naught should be my z naught value. And if I plug in 0 for x and 0, whoops, you can't see that. If I plug in 0 for x and 0 for y, my f of x, my f of 0, 0 is going to be 9. What's my partial with respect to x? Ooh, what is the partial with respect to x? Yeah. So it's negative 2x, but I'm going to plug in the x naught, y naught value. So I'm evaluating at 0, 0 times x minus 0 plus the partial with respect to y, which is negative 2y, also evaluated at 0, 0 times y minus 0. The reason I say this one's very unexciting is because it's not very exciting. We're just going to get 9 plus, if I plug in 0 there, I get 0 times x plus 0 times y. So I end up just getting literally the linearization L of x comma y equal 9. Which isn't surprising because literally our tangent plane is just the plane z equals 9. Right? It's not tilted left or right or backwards or forward. It's just a flat's not the right word. All planes are flat. It is a horizontal plane, right? It's living just like you took the xy plane and moved it up. Not a very exciting tangent plane, but a tangent plane nonetheless. And if you really wanted to, you could use this tangent plane to approximate this function at some value of x and y that's maybe terrible to plug in. For example, we could say I want to approximate. I'm going to try and make it terrible to plug in. F of negative 0.1 comma positive 0.2. That's probably not that bad. Plugging those numbers in is not that bad. But if you plug them in, it's kind of unexciting because there's literally nowhere to plug them in here. So we'd say, oh, well, that's approximately L of negative 0.1 comma 0.2, which is just not an exciting example. Let's change it up a little bit. Let's look at the same function, but instead look at a different point. Actually, let's look at a different function. That one's not very exciting. Go ahead and move it a little bit. So, moving on to a more interesting example. Sorry, There we go. Let's say we want to, one, we're first going to find linearization. And again, when you hear linearization, you can think tangent plane, right? You've got some surface function of f of xy equal to x cubed y to the fourth at the point 2, 1. I couldn't draw this. It's not very nice to draw, but we've got some surface. And all we're trying to do is find the tangent plane to that surface at that point. And again, it kind of gets, it's very kind of just a memorize this formula thing. There's not really a better way to do it. So we have that the linearization is, I don't think you need to write down the formula every time. I'm going to write it down, but you might want to not write this part down. It's up to you. It's going to be your f of 2, 1 plus the partial derivative of f with respect to x at that same point times x minus the x coordinate plus your partial derivative with respect to y at that same point times y minus the y coordinate. So let's see what we get. So plugging in 2 for x and 1 for y, 2 cubed is 8, 1 to the fourth is 1, 8 times 1 is 1. The partial with respect to x is going to be 3x squared times y to the fourth. We still have to plug in the point 2, 1 times x minus 2. The partial with respect to y is x cubed times 4y cubed. We still have to plug in the point 2, 1 times. So one more step here. The linearization of this function is 8 plus, let's see, plugging in 2 for x and 1 for y, we get 3 times 4 times 1. So 3 times 4 is 12. And then plugging in 2 for x and 1 for y, I get 2 cubed is 8 times 4 is 32. So there's your linearization. And as I said before, I don't recommend simplifying this. You totally could, right? You could simplify this. You could write it as L of xy equals 8 plus 12x minus 24 plus 32y minus 32. And then you can simplify it even more and get, let's see, negative 24 minus 32 is negative 56 plus 8 is negative 48. So 12x plus 32y minus 48. Here's why I don't recommend doing this, because of the next question I'm about to ask. Now we're going to use this linearization to approximate f of, what have I got here? 2.2 comma 0.9. So here's what I want you to see. If I plug in 2.2 here, 2.2 minus 2 is 0.2, and 12 times that is not hard to do. And 0.9 minus 1 is negative 0.1, and 32 times negative 0.1 is not that hard. On the other hand, 32 times 0.9 is kind of hard for me to calculate. 12 times 2.2 is not that easy to calculate, right? Those are harder things to do. So if you write it in this way, where you don't distribute those coefficients and leave x minus whatever and y minus whatever alone, you're going to be in a better situation if you're being asked to then approximate some value of the function. So doing it this way, I'm going to get 8 plus 12 times 2.2 minus 2 plus 32 times 0.9 minus 1, which is 8 plus 12 times 0.2 plus 32 times negative 0.1, which is 8 plus 2.4 minus 3.2. 2.4 minus 3.2 is negative 0.8. So 8 minus 0.8 is 7.2. And if you were to plug the actual numbers into a calculator, whereas f of 2.2 comma 0.9 would actually be 2.2 cubed times 0.9 to the fourth, which if we again use a calculator times, let's see, come on, calculator, not the stopwatch. Terrible. Can't get to my calculator. It's awful. So let's see. 2.2 cubed is 10.648. And 0.9 to the fourth is 0.6561. If we multiply this together, don't mess it up, we get 6.986. So pretty good, right? Our approximation wasn't that bad. It's definitely easier to calculate than if we didn't, right? So this is easy to calculate if you have a calculator, right? Like no big deal, 2.2 cubed, yeah. If you don't have a calculator, that's not the easiest thing to do. It takes some work. Yeah, okay, so let's look at a couple more. It's kind of the same thing over and over again. So tangent planes, aka linearizations, you're just using this idea over and over again. But let's look at a few more examples because it is worthwhile. Let's look at this one. Find the equation of the tangent plane to z equal to 4x squared minus y squared plus 2y at the point -1, 2, 4. What I want to point out is, even though we didn't write it, you should be thinking of this as your f of x comma y. So I want you all to try this one on your own. So here, I'll write down the formula, then I want you to give it a shot. So linearization is going to be f of -1 comma 2 plus the partial with respect to x times x minus the x coordinate plus your partial with respect to y times y minus the y coordinate. Go ahead and calculate that. Okay. So what is the function evaluated at -1, 2. What do we get if we plug in -1 for x and 2 for y? What do we get? Let's see. If I plug in -1 for x and 2 for y, -1, 2 is going to be 4 times -1 squared minus 2 squared plus 2 times 2. That's going to be 4 minus 4 plus 4, which is 4. Which they already told me, because that's really just the z coordinate. So they give you all 3 coordinates. They're telling you what f of x, y already is, or f of, in this case, -1, 2. So we're going to get 4 plus, okay, let's write down the partials up here. So my fx is what? What times x? Yeah. Favorite number, 8x. 8's my favorite number, not x. And fy going to be the partial with respect to y, which is 0 minus 2y plus 2. So I'm going to plug in these points. If I plug in -1, 2 to my partial with respect to x, I'm going to get 8 times -1. That is what that is right there. And I still have x plus 1 over here. Plus, same idea. If I plug in -1, 2 to fy, well, I'm just plugging in the 2 for y and getting -4 plus 2. That's going to be -2. Oops, I might write that in red. Sorry. Times the y minus 2. And that's kind of it. My linearization at x comma y is 4 minus 8 times x plus 1 minus 2 times y minus 2. And then we could use this to approximate something, some value of the function where x and y were close to the point -1, 2. So for example, we could approximate L of, I don't know, -0.8, comma, oops, yeah, that's right, comma 2.3. We plug that in, we're going to get that it's 4 minus 8 times -0.8 plus 1 minus 2 times 2.3 minus 2, which is something. It's 4 minus 8 times 0.2 minus 2 times 0.3. So I end up with 4 minus 1.6 minus 0.6, which is going to be, I don't know, 2.4 minus 0.6 is 1.8. So kind of interesting, I think, that if you move, we didn't move that far away from the point -1, 2, but our value went from 4 to 1.8. So seems interesting. It might be telling to see what the graph looked like. Yeah. So just to kind of see things here, it's kind of interesting. So I'll move this over for 1 second. If we graph this thing, what do we got here? 4x squared. And you can't see it yet. Just 1 second. Minus y squared plus 2y. Well, that looks crazy. It looks pretty crazy. There's our surface. We zoom out. It's kind of bonkers. If we go in, you can kind of see that, oh yeah, like if you're making even small changes in x and y, might lead to some pretty drastic changes in your function output value. So it's kind of hard to get, like, if we're looking at what we're looking at x, sorry, we're looking at the point -1, 2. So if I go back in the x direction, which is the red direction, so if I go over to -1 and up over to 2 in the y direction, kind of like somewhere on the surface here. And so you might kind of, oh, can I do that? Can I do this? Does this work? Does it show me the point? Oh, okay. I want the y value. That's fine. It's okay. So, right, if I look at that point there, if I go up to the surface from there, it's pretty high up already. And any small change is going to really get magnified because of how steep the surface is. So looking at the surface, it's not surprising that this small change in X and Y from our inputs gives a relatively large change in our output. All right. Let me do one more thing. So, oh yeah, I know. So I was looking at your homework assignment because it's good to be aware of your homework assignment. There is one other kind of thing I just wanted to point out. The last couple of questions have to do with eigenvalues and eigenvectors on your homework, and I thought it seemed worthwhile. So, just as a reminder, I know it's been a little while since you talked about eigenvectors and eigenvalues. But we might have slightly at the beginning of the quarter, but otherwise it's been since you probably took it. Might have been over the summer, might have been in spring, might have been way before that. So you might not remember how they work. So here's what I want to remind you of. For matrix A, if lambda 1 is the eigenvalue associated with V1, the eigenvector, and similarly, lambda 2 with V2. So lambda 1 and lambda 2 are both numbers. V1 and V2 are both vectors. The thing that is true is the following. It is true that A times the eigenvector is equal to the eigenvalue times the eigenvector. And similarly, A times the second eigenvector is equal to the second eigenvalue. So for example, I don't have an example off the top of my head, so I'll make one up and then we'll probably just fine. Sure. If our matrix is, I really should, sure. Trace determinant 5, -6, okay. 4 minus 10, okay. 2, 5, that'll work out. All right, cool. We'll talk about, I said 2 words, trace determinant. We will talk about those later. There's a nice fast way of finding things when you have a little more practice. But for this matrix, we can find the eigenvalues by calculating the determinant of A minus lambda I, setting that equal to 0. So that's going to be the determinant of 1 minus lambda, 2, 5, 4 minus lambda. So that's equal to 0. So look what we get. We're going to get 1 minus lambda times 4 minus lambda, minus 2 times 5. We multiply this out, we're going to get minus lambda times minus lambda is lambda squared. Minus 4 lambda minus 1 lambda is minus 5 lambda. 4 times 1 is 4. 4 minus 10 is negative 6. So factoring this, you get lambda minus 6 times lambda plus 1. So your eigenvalues are positive 6 and negative 1. Often, if they're both positive, we say the bigger one, the lambda 1. If one's positive, one's negative, we say the positive. Usually the bigger one is lambda, although it doesn't really matter. Okay. Let's also find the eigenvectors, because I really just want you to remember and see what these things mean. So, find the eigenvectors, we're going to calculate the following. So to find V1, here's what we need. We need the matrix times the vector equal to the eigenvalue times the vector. Well, I know all the things except for the eigenvector. I know the matrix is 1, 2, 5, 4. I don't know the eigenvector, so I'm going to call it x, y. I know the eigenvalue is 6. My eigenvector again is x, y. So I'm going to use the first row's worth of equations and get 1 times x plus 2 times y equals 6 times x. You could also use the second row. It'll work out just fine. Isolating y, 2y equals 5x. And I would probably stop there. Here's the fun fact, maybe. The useful fact. When you get to this point, you could solve for y in terms of x. But if you leave it here, you can just say, oh, my eigenvector, you're going to let y equal the coefficient of x and x equal the coefficient of y. So that my eigenvector is 2, 5. Or literally any multiple of 2, 5 that you want. If you decided you wanted to solve for y and say y equal to 5 halves x, you could say x is 1 and y is 5 halves. Or you can make the nicer choice and say x is 2 and y is 5. So that's our eigenvector. And again, here's what this really means. This means that A times this eigenvector, I just want to write it down. So 1, 2, 5, 4 times my eigenvector is equal to, let's see, 1 times 2 is 2, 2 times 5 is 10, 2 plus 10 is 12, 5 times 2 is 10, 4 times 5 is 20, 10 plus 20 is 30. And look, that's exactly 6 times the vector 2, 5. That is the whole point. If something's an eigenvector, if you multiply the matrix by it, you just get the eigenvalue times it. I'll say it one more time. If you have an eigenvector, the matrix times the eigenvector is always equal to the eigenvalue times the eigenvector. So in this last homework, in the second last homework question, where they tell you the eigenvectors and the eigenvalues and they don't tell you the matrix, the point is that when they tell you you have something like A times the first eigenvector plus the second eigenvector, the idea is to be like, oh, well, that's A times the first eigenvector plus A times the second eigenvector. And even though I don't know what A is, I know that A times the eigenvector is the first eigenvalue times the first eigenvector. And A times the second eigenvector is the second eigenvalue times the second eigenvector. So in this particular example I'm doing, I would end up getting lambda 1, which is 6, times the first eigenvector, which is 2, 5, plus lambda 2, which I forgot what lambda 2 was, it's negative 1, times the second eigenvector, which we didn't find yet. So whatever it is, that's what you would put in there. We could find it, it's not too hard to find. I guess what I could, since I've got 1 minute left. So just so you can see what the second eigenvector is, I'm trying to solve A times V2 equal to lambda 2 times V2. I'm really trying to solve 1, 2, 5, 4 times my second eigenvector equal to negative 1 times my second eigenvector. And that's going to be 1 times x plus 2 times y equal to negative x, or 2y equal to negative 2x. And I could divide both sides by 2 here and get y equal to negative x. So my eigenvector is x is 1, y is negative 1. So that's kind of the point that they're trying to get you to see with that those last couple of questions, is that when you multiply a matrix by its eigenvector, you just get the eigenvalue times the eigenvector. Always true. That's what's special about eigenvectors. And yeah. All right, I can stop talking. 3 o'clock.